Hello. Today we're going to be talking about measurement in the laboratory, and more specifically how to correctly round and measure to the correct number of significant figures. The first thing I want to talk about is accuracy versus precision. Now, accuracy is being close to the real actual value. So what's the real actual value of different units of measurement? Well, it turns out in France there is an International Bureau of Measurement, and they have that little mass right there that you see, and that's the standard kilogram, and that weird shaped object is a standard meter. And from that, every other kilogram mass and every other meter length is measured, or measured from something that's measured from that, or measured from something that's measured from something that's measured from something that's measured from that. But those are the standards for the world of what is a meter, what is a kilogram, and they have others for the different units of measurement. Precision is the ability of a measurement to be reproduced consistently, so using different measuring instrument or different observers or different anything. And it's described on a piece of paper by the number of digits that are used to express the value. So how many decimal points is it measured to? So let me give you an example. If I handed you a meter stick that was misprinted, so it was actually 110 centimeters long, but it was just printed from 0 to 100 over that 110 centimeters, you could still make very precise measurements using the millimeter marks because it's broken down into a fairly small unit, millimeters. However, the accuracy of that stick would be very poor because 1 real centimeter would not be equal to what the stick was saying was 1 centimeter. So that's the difference between precision and accuracy. Precision is how precise can you measure it, whereas accuracy is the actual thing or not. Okay, rounding. I assume you all know how to round, and if you don't, well, here we go. Any value of, we're talking about the last digit of a number, if it's 5 or greater, then you round up. If it's 4 or less, then you round down. And what if it's 4.5? Well, you can't have 4.5 for the last digit because then that's 4.45 or 4.5, and then the 5 becomes the last digit. So if I gave you the number 7.7 and asked you to round to the nearest whole number, the last digit 7 is larger than 5, so you would round up to the nearest whole number, which is 8. If I gave you the number of 8.2, 2 is smaller than 5, so it would round down to the nearest whole number of 8. And what if I gave you a number like 25.45 and I said round it to the nearest whole number? Well, some people would do this. I want you to know there are people that do this. The 5 would round the 4 up to a 5, and then you would use that to round to 26, which is not true. 45 is less than 50, so it rounds down. You can't use a digit to round 2 decimal places over. So I can't use that 5 to round the 25 to a 26. I can only use the 5 to round it up to 25.5, or it rounds down to 25. Okay, how do you read an instrument? You're always going to record the measurement to the most precise value you can. So if something is, like a triple beam balance, is marked to the nearest tenth of a gram, you can estimate between the tenths to the nearest hundredth of a gram. So in this example, how many grams does this triple beam measure? So I've got 373 point, and it looks like 0.3, and then I can estimate one more decimal point, so I get 0.34 grams. So the correct way to measure this would be 373.34 grams. That last digit is an estimate. Okay, significant figures. Significant figures refers to the number of digits in a number that are meaningful in terms of the measurement made. So the last digit is assumed to be an estimate, but it's still a significant digit. So let me give you an example of what I'm talking about. If I said I had an object that was 4.2 grams, what that means is because of rounding, it has an actual mass of somewhere between 4.15, anything 4.15 and bigger would round up to 4.2, and 4.24 or smaller. So the 2.4 would round down to 4.2. If I'd written that as 4.20, I'd be implying that there was more precision than was actually involved in the measurement. And if I reported that it's just 4, well, I'm not giving you the most precise number I could. 4.2 has two significant figures, the 4 and the 2. If I had measured 4.20, that would be three significant figures. But I didn't measure to 3, I measured to 2 significant figures. All right, there's a whole bunch of rules to this. They're on your paper. We're going to go through them. You ready? Rule number 1. All non-zero numbers are significant numbers. So for example, if I had 14.155, I'm going to count the digits. I've got the 1, the 4, the 1, the 5, the 5. There's 5 significant figures there. If I gave you a number like 12.1, the 1, the 2, and the 1 are significant. So there's 3 significant figures. Rule number 2. Zeros between other numbers are significant. So if I have a 0 somewhere in the middle, like 1,107, that 0 is significant, so that number has 4 significant figures. If I have 50.002, though all those zeros in the middle are significant, so this has 5 significant figures. All right, next set of rules. Zeros that precede or come before the first non-zero digit are not significant. So if I give you the number 0.000163, all of those zeros, because they come before the first non-zero digit, are not significant. So this is measured to 3 significant figures. 0.006801, the 0 in the middle is significant, the zeros at the front are not, so it has 4 significant figures. Next rule. Zeros at the end of a number are significant if they're to the right of a decimal point. So 0.2000 has 4 significant figures, the 2 and then all of the zeros. The 0 to the left of the decimal point is not significant. And then 0.050120, the zeros before the 5 are not significant. The zeros in the middle and after the decimal are significant. Okay, now we get to the complicated rules. Zeros at the end of a number may or may not be significant if the number is written without a decimal point. So remember the last rule, it was if there was a decimal point. And this one we're saying there's no decimal point. So if I gave you the number 400, we don't know if that's to the nearest unit, the nearest tens place, the nearest hundreds place. No idea. So how do we fix this? Well, here's what we do. You write it in scientific notation. So 4.00 times 10 to the second has 3 significant figures, and that would be measured to the nearest ones place. 4.0 times 10 to the second has 2 significant figures, and that's measured to the nearest tens place. Or 4 times 10 to the second has 1 significant figure, and that was measured to the nearest hundreds place. So if we use scientific notation, we can use all the regular significant figure rules. But if I just give you 400, you really can't answer that question. If we start multiplying and dividing numbers, we need to be able to figure out how many significant figures your answer should have. And this is why I'm teaching you significant figures. Because at some point this year, you're going to raise your hand and you're going to say, Mr. Hughes, what do I round this to? The nearest tens, hundreds, thousands? Well, it turns out there's an answer without me having to answer, and that's use significant figures. So with multiplication and division, if you're multiplying or dividing numbers, the calculated result may be no more precise than the least precise data used in the calculation. So if I multiplied 13 times 2.5, the answer I get would be 32.5 on my calculator. But 13 has 2 significant figures. 2.5 has 2 significant figures. So my answer can only have 2 significant figures. So you would need to round it to 33. If I multiply 0.52 times 0.8, your calculator would tell you the answer is 0.416. But 0.8 only has 1 significant figure, so your answer can only have 1 significant figure, so you have to round it to 0.4. If I multiply 21 times 0.013, both of those have 2 significant figures, so even though your calculator says 0.273, you should write 0.27. Now you may think you're cutting off too much data, but the reality is you can't be any more precise than your least precise measurement. When you're adding and subtracting, the rule's a little different. The calculated result may have no more digits to the right of the decimal than the data with the fewest digits to the right of the decimal that went into it. So 13 has no numbers to the right of the decimal. 2.5 has 1 to the right of the decimal. The calculator says 15.5, but because I had none to the right in 13, my answer can have none to the right of the decimal. So I have to round it to 16. With 0.52 plus 0.8, 0.52 has 2 to the right, but 0.8 only has 1 to the right of the decimal. So my answer can only have 1 to the right of the decimal. So even though the calculator says 1.32, you should write down 1.3. 21 plus 0.013, 21 has none to the right, 0.013 has 2 to the right, you can't have any to the right, so the answer is 21. That about wraps that up. If you have any questions, write them down on your paper. We will go over this a lot in class tomorrow, so if you're still confused, don't worry, we're going to do a lot of practice with this and you'll be able to ask me questions.